So we're going to look at the intermediate value theorem. Before we get into that specifically, I want to look at this function here. We have a piecewise function. This is a little bit of review. But I want to look at this function here and determine which values f is not continuous at, and then also which of the discontinuities are removable. Now, that we actually have done, but I want you to think about this terminology. What do we mean when we're talking about a discontinuity that is removable? Yeah, it's a hole, okay? Removable discontinuities are holes. Things that we can't remove are the asymptotes, okay? Or a large jump of some sort, okay? So let's first of all, it says a little hint. Let's graph this, and then find out where this is continuous, okay? So as we're graphing a piecewise function, you can treat each part separately. Okay, notice the range here. It says when the absolute value of x is less than 1. Okay? Now, can you put that in kind of another sense that may make a little more sense to us? How else could we say that? Absolute value of x is less than 1. Okay, yeah, another way that you could say this would just be like this. X is between -1 and 1. Okay, so on our graph, we should mark off -1 and 1. Okay? And it would be good to have, anytime you're dealing with a piecewise function, you want to try to find out where the ends end up. Okay? So if I were to actually plug in -1, obviously I'm going to have an open point there because it won't actually equal -1. But when I'm graphing this, I'm going to find the ends there. So if I plug in a -1 here for tangent of pi x over 4, so -1x, so -1 pi over 4, or negative pi over 4, what is the tangent of negative pi over 4? -1. Which is it? Do you guys remember? -1. Here's negative pi over 4.
1.
All students take calculus, so it is negative. -1. Okay? So let's put this on here as an open point at -1, -1. Okay? How about when x is +1? You'd have a positive pi over 4, right?
Yes.
Square root of 2 over 2? That's what sine and cosine both are. So tangent equals 1. There we go. Okay, so here's another open point over here. Okay? If we plug in 0, since that's in the middle here, we could plug in a couple of different things here. If we plugged in 0, what's tangent of 0? 0. Okay. And from what you guys know about the tangent graph, you know this is going to look kind of like this, right? So now you have it's x when x is greater than or equal to 1. Okay, so let's do that one in blue. And the absolute value of x is greater than or equal to 1 is x is greater than or equal to 1, or x is less than or equal to negative 1. Okay? So, what's this going to look like? Okay, yeah, this is the line y equals x. It picks up in that point, and now we're moving at a straight line y equals x, right? And same thing over here on the other side. We have that. Okay? Any questions? Okay. So, where is this function not continuous? Nowhere. It's always continuous. Okay? It's always continuous. So, that would just be our conclusion. It doesn't have any holes, doesn't have any asymptotes. This is just always continuous. Okay?
How do you spell asymptotes?
Asymptote is ASYMPTOTE. Asymptote. It's a weird spelling. Okay. All right, now in our previous lessons we talked about how to show that something is continuous on a closed interval. Being continuous on an open interval was kind of easy to tell because you just looked for any points of discontinuity, any holes or asymptotes. The points that can be a challenge are on the closed interval are those endpoints. So we said that on the left-hand side, like here at A, if the limit as the function approached A, or as x approached A, from the right equaled the same thing that f of A equaled, then we said it was continuous from the right at A. And then over here on the right-hand side at B, if the function was continuous, or I'm sorry, if the limit of the function as x approached B from the left-hand side equaled f of B, then we said that it was continuous from the left at B. So once you said that, okay, it's continuous on the open interval, it's continuous from the right at the left side, and it's continuous from the left at the right side, then we know it's continuous around the closed interval. So that's the first condition here in our intermediate value theorem. Okay, it's got to be continuous on the closed interval AB. Now, here's what the intermediate value theorem says. If k is any number between f of A and f of B, so notice we're talking about y coordinates here. K is any number between f of A and f of B, then there's at least one number C in the interval from A to B such that f of C equals k. Alright? So you can see here we have f of A and f of B. In this case, f of A happened to be greater than f of B. That doesn't have to be the case. We just have these two values. we could pick any number between these two values and call that k. And we know that there will be at least one place in this interval from a to b where when we evaluate the function, we'll hit k. All right? Now, in this case, there happens to be 3 different instances. Okay? So notice here, our intermediate value theorem does not tell us how many times. It just tells us we're guaranteed to get at least one time, one value of x that will give us that number k. All right? In this case, like we said, there exist 3 c's that give us f of c equal to k. Now notice here, in this case, this is why we need the continuous nature of this function. If it's not continuous, it's possible that we could have something like this. Here we have f of a and f of b. Okay, f of a and f of b. But because it's not continuous, there is this value of k that we could pick where it doesn't matter what we plug in, we're never going to get this value of k within the interval. All right, and that's again because it's not continuous. All right? So that's the basic idea of this intermediate value theorem. Let's do an example of this with an actual function and see how this works. Since we've already done this, let's look at our work above here, okay? Looks okay.
Mr. Nixon?
Yes?
Just wondering, wouldn't this theorem not work if there was a hole at C2, for example, on the first example? Because technically it would, there would be a C value, but there'd also be a hole.
Hang on, you're asking about C2 here?
Yeah, this theorem is to figure out if the function is continuous, right? And if there was a hole at C2 or something, wouldn't it still...
No, this does not tell us it's continuous. It being continuous is a condition for this to be true. Yeah, if you guys remember conditionals back in geometry, maybe you studied conditionals, the if-then statements. The condition here is that it has to be continuous on the closed interval, and k has to be between f of a and f of b. There are 2 conditions that have to be met here. The conclusion is that we get at least one number that will give us f of c equals k. Okay, I'm glad you asked that though. I want to make sure that we've got that straight. All right, so let's actually look at this original function that we were working with at the beginning. We already determined that this is continuous actually for all real numbers. Okay, so let's go ahead and pick an interval. Someone give us an interval.
What is interval?
An interval, just a range of numbers for x to equal. You want x to go from what to what?
-3 to 2.
-3 to 2. Okay. So let's suppose we have -3 to 2 as the interval for f of x above. Okay? Well, first of all, because we know that f of x above is always continuous, then we automatically know that it will be continuous on the closed interval -3, 2. Okay? All right? So that's the first condition. Since f of x is continuous for the real numbers, okay? I should say x in the real numbers. Then it is continuous on the interval from -3 to 2. Okay? Everyone with me so far? All right. So, secondly, we're going to let k equal something. Now, before we can pick a value for k, we do need to make sure that it meets the second condition. K has to be between f of -3 and f of 2. Okay? So, before we decide on a value for k, what is f of -3? If it's -3, absolute value -3 is greater than 1, so we're using this equals x. So you're right, it would just be -3. Okay? F of 3 is -3. And what's f of 2? 2. So, as long as we pick a number between -3 and 2, I know there's at least one value where f of x will equal that number. Okay? So, why don't we pick, let's let k equal 1/2. Okay? Alright, so now that we have this here, we're going to let k equal 1/2. So, oops, a little big. Let's change this back down to a reasonable size. Okay, so k equals 1/2. Alright, now just by looking at this, we can see that there is one value where our graph does hit the 1/2. Okay, we can see it on the graph, but let's go ahead and calculate what that would be. All right, now, one thing where looking at the graph is useful is in what in this case? How is it helpful to see about where it is?
You know, formula,
Okay, yeah, we know which part of that piecewise function, it's the tangent of pi x over 4, that's the one that we're going to be looking at, okay? So, we know that tangent of pi x over 4 has to equal 1/2. Okay? Does that make sense? All right, so here's where we may have to use the calculator a little bit, make sure that we are in radians. Okay? But notice here, we know that the value is going to be between 0 and 1. Just by looking at the graph here, we know it's going to be between 0 and 1. All right, but we can use our calculators and figure out what it is. So go ahead and solve that here. A little bit of practice solving trig equations. Okay, so when we do the inverse tangent, you're getting to 0.463647,609. Remember, don't round anything until you get to the end, until you get to your final answer. So that's pi x over 4. So what does x end up equaling? 0.590?
Yeah.
Good.
Yeah.
Alright,
Is it?
so our intermediate value theorem ensured us that we would get an answer. Then we were able to use algebra in order to actually find that answer. Okay? So, Winnie, what were you going to ask?
I don't know, because I used 3.14 as pi, like number for pi, so I got like 0.591. So I guess like there's a...
Okay, yeah, I would, if you're going to just type it in, I would at least do like 3.14159.
Okay.
You know, something like that, give it more decimals. Or just above the exponent button on your calculator is the pi button. It's the button above the division sign.
Yeah, this one.
Yeah, if you hit second, that'll put pi in and it gives the unrounded
Thank you.
value for it. Okay? Alright, so that's the basic gist there of the intermediate value theorem. It's ensuring, it's like we had mentioned a little earlier when we introduced this is an existence theorem. It's just telling us that something exists before we go through the hassle of actually trying to find it. Okay? It's ensuring that it will exist. And sometimes, you know what, just knowing that there is a value that works is all we really care to know. We don't really care what the value actually is. We just want to make sure that it would exist there somewhere. So I mean that is a possibility as well. Okay? Questions? All right, good. Yeah, it might have been good to actually show that upper and lower boundary. Switch over to here. Okay. For our intermediate value theorem, our interval went from -3 to +2, and on the y-axis that means it was going from -3, so that was this point here, up to +2, +2 here. Okay, so we knew it was, here's f of 2, and we knew that this right here was our f of -3. Okay, so we knew k was between those two.
And when you say minus 3, 2, do you refer to, suppose we have minus 3, 2 as the interval, do you refer to the y or the x?
Those are the x values. Yeah, those are the x values.
So why is the interval for fx instead of x?
No, this interval right here is saying that x is between -3 and +2. Those are x's. The k has to be between the -3 and the +2, because those are f of -3 and f of 2. And in this particular function, it just happened to be -3 and 2 again.
Mm-hmm.
Okay, and that may be where the confusion is there, but okay.